Great. Well, thank you so much. Let's start. Shall we start? I think people will trickle in. Thank you,
Okay.
Hansen Sue, for joining us on our Community Day. So appreciated. I'm so excited about this presentation. Just a very quick bio of Hansen. Hansen is a historian and sociologist of technology and a curator of the Computer History Museum, Software History Center. And he works at the intersection of the histories of personal computing, graphical user interface, object-oriented programming, and software engineering. Hansen received his PhD in science and technology from Cornell University. Yay, Cornell. And with a dissertation entitled AppSmith, Community, Identity, Effect, Ideology Among Cocoa Developer from Next to iPhone. Previously, he worked for Apple. Yay, Apple. From 1999 to 2005, where he contributed to release of Mac OS X from public beta through 10.4 as a quality assurance engineer for Cocoa Framework Group. He also received his bachelor's degree in electrical engineering and computer science from UC Berkeley in 1999, and his master's of arts in history from State University of New York, Stony Brook in 2007. Hansen, welcome to our Community Day, and thank you for presenting to us.
Thank you, Tina. So let me start sharing my screen now. Okay, can everyone see that? Okay, let me play the slideshow. Can everyone see that?
Yes.
Okay, and so, okay, thank you for that introduction. I guess I don't really need to talk about my background, so I'll skip this slide. So first off, just a little bit of introduction to the Computer History Museum. Our mission is to decode technology, its computing past, digital present, and future impact on humanity. As part of that mission, we preserve and present for posterity the artifacts and stories of the information age. We are a nonprofit organization. Our physical presence is in Mountain View, California. We have a 4-decade history. We're home to the world's largest collection of computing artifacts that includes 75,000 physical artifacts and 150,000 items of code and recorded media. So that means that we collect hardware, we collect software, we collect audiovisual media, and we also collect paper documents. And so in addition to our exhibits, which you can visit whenever we open up at our building in Mountain View, we also have educational programs. We have our CHM Live speaker series, our event series, which is ongoing, and we continue to have had those online during the pandemic. We also have a research archive, the Shostak Research Archives, which is a building located in Fremont. And so this is where researchers can go to do historical research on our archives. A quick sort of overview of the history of the museum itself. It was originally founded by Digital Equipment Corporation in 1979 as their own corporate museum. It became the Computer Museum in 1984 in Boston's Museum Wharf. And so the sort of a West Coast branch of the Boston version of the Computer Museum opened up at Moffett Field here in 1996, and that was spearheaded by Len Shostak, who is the namesake of the Shostak Center in Fremont. And he's a local Silicon Valley entrepreneur, and he was teaching at Stanford at the time, and he realized that a lot of his students didn't know much about computer history, and so he really wanted to create an institution for computer history centered here in Silicon Valley. And then, so he made a connection to the Computer Museum in Boston, and he arranged to have the main collection of the Computer Museum to come out here to Silicon Valley. And so that was stored at Moffett Field until the current building was purchased. And that was purchased from Silicon Graphics in 2002 during the dot-com crash. And then the Boston Museum closed in 1999, and then we became the Computer History Museum. We took over the mantle. So we have two main exhibits. Our primary permanent exhibit is Revolution, the first 2,000 years of computing, and that opened in 2011. It has 19 galleries ranging from calculators through punch cards, analog computers, all the way up to mobile computing and the internet and the web. And our most recent long-term exhibit is Make Software Change the World. That opened in January of 2017. All right, so I'm going to sort of our tale today. Today, I'm going to talk about sort of a brief history of interactive computing, and in the sense of, the way that we all use computers today is we do something with a computer, and it's interactive. It presents feedback directly to us in real time. Now, this hasn't always been the way that computers worked. And if you go back to the 1960s, for instance, most computers of that era, what we today call mainframes, worked in a very different way, called batch processing. And this involved the use of punch cards. So if you see, there's an example of a punch card in the corner there. Typically what a user, somebody who wanted to use a computer would do was they would, so let's say you have a program and you write your program on paper, and then you give that program to a punch card operator who was almost always a woman, and she would type in the program, punch that into a stack of punch cards. And so these are basically these cards with holes in them, and the position of the hole sort of allows it to represent different information. And so you would then take that big stack of cards and you would go to give that to the computer operator, and the operator would take that stack, and then they would put your stack of cards into a queue in a big, large batch along with a bunch of other people's programs, and they would run that entire batch all together. And the reason that they did that was because back in those days, the mainframes of the time were extremely expensive to purchase, to run, and to operate. The average cost of a mainframe was probably about $1 million. IBM, the main the main company that most people bought computers from, mainframes from, actually leased the computers as its main business model. So you actually wouldn't purchase the computer outright. You actually just leased it from IBM. And with computing time that expensive, you wanted to maximize your investment by basically keeping it running all the time. And so in order to do that, the most efficient way to do that for the computer was to basically put everybody's programs all together in a batch like that and sort of run that. So the throughput through the machine was as high as possible. And so this was really great for the kinds of applications that mainframe computers were mostly used for in the 1960s. And a lot of these were like financial applications, accounting, payroll, sometimes scientific calculations as well. And this sort of use case was a good match for batch processing. But of course, it has certain downsides. So once again, the average user doesn't have any personal access to the machine. What they do is, they give their cards to the operator, and then the operator gives them a printout the next day. So what happens if, if anyone who's ever written a program here might know, is it's actually very easy to make simple typos and mistakes. And often, just one little typo can essentially ruin the entire program. And if you had to wait an entire day to discover that you made one little mistake, well, that's actually very inefficient for the user. So although this was a very efficient way of organizing, the computers, of optimizing the computer's resources, it was a very, very inefficient way of optimizing the user's time. So next, I'm going to talk about some of the early interactive computers. Even though most computers operated in dispatch mode, there were interactive computers even at that time. And going back as far as the very end of the Second World War. So one of the earliest computers that operated in real time was called the Whirlwind, and that was built at MIT. And that was used for, that was sort of the prototype for a larger system called SAGE, which was the nation's nuclear air defense system. And so, having a direct military application, it has to operate in real time, because if it's there trying to detect incoming Soviet aircraft, well, you can't wait 12 hours to notify that, oh, we're being attacked, right? So this machine was built for that kind of purpose, and this had a graphical CRT display, a cathode ray tube display that was basically a radar screen. And it also had one of the earliest pointing devices called a light gun. And if you could see, there's a picture of the user there using the light gun. He's pointing that gun at the radar screen. And what that does is the gun will detect a blip which shows up as a point of light on the radar screen, and then feed those coordinates, those numerical coordinates, to the computer. So sort of this, the Whirlwind then sort of led to several additional computers that were developed at MIT's Lincoln Laboratory, led by a researcher named Wesley Clark. And so this is the TX0 and the TX2. And the TX0 was sort of like a miniaturized, transistorized version of the Whirlwind. The Whirlwind had used vacuum tubes, so it was very big, very hot. The TX0 was much smaller. And then that then was built upon to create a larger computer called the TX2. And so these were machines that were built at MIT for military and scientific research. One of the most notable things about the TX2 was that it was the computer that a man named Ivan Sutherland used to write one of the first interactive graphics programs called Sketchpad, and that was his thesis in 1963. And that Sketchpad is in a way the sort of granddaddy of all graphics programs. Wesley Clark also went on to build another computer called the Link, which was primarily made for biomedical research. So this sort of line of smaller interactive machines led to what we now call mini computers. So mini computers are smaller, cheaper, and simpler to use than mainframes. They have interactive real-time control. And they're typically used by a small department in a university or a company. And they're often typically dedicated to a single task. So, probably the most notable mini computer company was Digital Equipment Corporation. And that was founded by Ken Olsen and Harlan Anderson, both who had been at MIT. Olsen himself had been at Lincoln Lab and had worked on the TX2. And he decided to start Digital Equipment Corporation in 1959, and specifically, DEC doesn't have the name computer in its name, because since IBM was so dominant in the mainframe world, everybody thought that if you tried to go up against IBM, if you had computer in your name, that meant you were going up against IBM, and that would guarantee that you would get crushed by IBM. So they sort of avoided that. And their first products weren't actually computers. They actually made circuit modules that could be used to make computers. But in 1961, one of their engineers, Ben Gurley, did use their modules to create their first computer, the PDP-1. And PDP stands for Programmed Data Processor. So that was based on the TX0 and TX2 designs, and it had an 18-bit word length. Once again, Programmed Data Processor also doesn't have a computer in the name. So like these machines that at MIT that it was based on, the PDP-1 was interactive. So that meant that you could actually type on this typewriter console and you get a real-time response printed out line by line as you typed. It also came with an optional CRT graphical display. So this led to some really interesting and really groundbreaking applications. And DEC donated PDP-1 back to their alma mater, back to MIT, and a lot of the grad students there got to play with it, hack on it, and write programs for it. And one of the most interesting programs that came out of that was a game. Probably one of the first interactive computer games, and that was written by Steve Russell. It's called Space War. And so there's actually a little bit of a picture of Space War on the screen there. And in Space War, there's two players. You control two spaceships, and there's realistic physics. So if you have to either accelerate or decelerate and use your thrust. It's kind of like if you've played Asteroids. That's kind of how the controls are. But instead of blowing up asteroids, you're actually trying to blow up each other. And there's like a sun in the middle, so that creates gravity. So you can sort of slingshot around the sun. Use the gravity to accelerate you, etc. And yes, Space War was really emblematic of the kind of hacker culture that surrounded the MIT Computer Lab, and that eventually became the topic of a pretty famous Rolling Stone article in 1972. So DEC had discovered this whole new market for smaller, cheaper, and interactive computers. And by cheaper, we're still talking about, initially the PDP-1 was sold in the range of around $100,000 in the beginning. That's still cheaper than a mainframe, which was 10 times that. But eventually, mini computers would drop down to like the tens of thousands of dollars. So on the left here, you see the PDP-8. So that was one of the DEC's best-selling computers in its early years, and that was initially built to monitor nuclear reactors. So that sold over 10,000 units over 25 years, and so that was actually a hit, in those times. And that really showed that there was a really big market for this new kind of computer. And the actual designer of the PDP-8, Ed DeCastro, decided to start his own company called Data General. And they came out with a computer called the Nova in 1968, which actually sold for less than $10,000. So that was sort of a new price point. And DEC ended up responding with their own competitor to the Nova, which was the PDP-11 in 1970. And PDP-11s became fixtures in a lot of university departments. And it was also the computer on which the Unix operating system was first developed at Bell Labs. So that's another interesting bit about the PDP-11. So other makers were starting to get into the computer business because of this new use case, because machines like this could act in real time, which meant that they could be used for things like process control in chemical plants, for instance, or for, say, surgery. And so Hewlett Packard, Hewlett Packard had been founded in the early 20th century as a maker of scientific instruments, not as a computer company. But in the 60s, they realized that computer control of scientific instruments was becoming really, really important. So they created their first mini computer, the 2116, as one of these controllers for their instruments. But then they found that people wanted to buy it just as a general purpose computer as well. So that's really what got Hewlett Packard into the computer business. And today, that's their primary business. So next, I'm going to talk a little bit about the role that the Defense Department's Advanced Research Projects Agency, or ARPA, which now is called DARPA, Defense Advanced Research Projects Agency, played in really spurring the research and development of interactive computing. So while mini computers was one way of getting interactive access to cheaper computers to more users, another way was to take a mainframe and to allow multiple users to share that mainframe. So that's a concept called timesharing. And that was really pushed by the director at ARPA, who is the head of its computer research department, which is called the Information Processing Techniques Office, or IPTO. So that was a man named J.C.R. Licklider, and he was a psychoacoustics researcher who had helped establish MIT's Lincoln Laboratory, and he had worked on the stage and was familiar with the TX0 and TX2 computers. And because he had had that experience, he believed that that was really the way that all computers should work. And so he was kind of dismayed when he realized that the mainstream of computers in the business world, led by IBM, was really focused on batch processing. And so he felt that given left to its own devices, the computer industry really wouldn't really focus on developing interactivity. So in 1960, he wrote a very influential paper called Man-Computer Symbiosis, in which he argued that in the future, humans would be tightly coupled in a beneficial relationship with computers, and one which would amplify our intelligence. And so being able to interact with a computer in real time was a critical piece of this vision. So Licklider had been, because he had been part of the academic MIT community before joining ARPA, he had a lot of close ties to academics at MIT and at other institutions. And so he kind of used ARPA and his position at ARPA to fund the research of the computer scientists that he saw that would further his goals. And so a lot of the cutting edge research in the US in computer science in a number of areas, including artificial intelligence, computer graphics, networking, and time sharing, were all funded by Licklider and his successors at ARPA. And one of those, and another thing is that he tended to focus the big grants on particular institutions that he would designate as centers of excellence. So MIT, Stanford, and Carnegie Mellon University got a lot of the grants that came from ARPA. Utah, UC Berkeley, and UCLA also got grants, and Utah in particular became sort of the center for computer graphics research because of that. So a little bit more about time sharing. So time sharing is essentially a way to take one computer and to sort of split up its central processing unit's time among multiple users. So that's called a time slice. So every, say, 10 nanoseconds or something is devoted to this one user, and then the next one is devoted to a different user. And Each of these users are actually logged into that computer remotely via a terminal. So initially those terminals were things like teletypes, so little typewriters with keyboards connected to a phone line. Later on, they became video terminals or so-called glass teletypes with a CRT screen instead. But the idea is basically the same. The user interacts with the machine by typing on it, and that would go over the phone line remotely to this larger host computer mainframe. And the technology for this really required a lot of research in operating systems development. And a lot of that went on in these various centers, universities that were funded by ARPA. So MIT was a big center of this. And one big proponent of that was John McCarthy, who is better known as one of the founding fathers of artificial intelligence. And McCarthy saw time-sharing and interactive computing as a crucial component for the development of AI. He had created the Lisp programming language for AI, and Lisp is an interactive language. You actually type with it and write code in it interactively. So he really believed that interactivity was key for developing AI. So he helped start this project, CTSS, the Compatible Time Sharing System at MIT with Fernando Corbado. Later on, another time sharing project at MIT was part of Project MAC, which sometimes stands for Machine Aided Cognition, other times stands for Multi-Access Computer. It actually has multiple meanings. And the system that came out of that was called Multics. And that was a joint collaboration between MIT, General Electric, which made mainframes at the time, and Bell Laboratories. That project ran into some difficulties and GE eventually pulled out. And so, some of the people that had been working at Bell Labs, including Ken Thompson and Dennis Ritchie, they had been worked on Multics, and they became very disillusioned by the Multics project. It was just too complicated. So they actually decided to create their own smaller version of Multics, which they called Unix. And so that's sort of how the genesis of Unix came about. At Berkeley, another time sharing project called Project Genie was being worked on, and that was led by Peter Deutsch, Butler Lamson, and Chuck Thacker. And that was being developed on an SDS 930 machine, which then became the 940 once they added time sharing to it. Other notable time sharing systems were the PDB-10 with its 10x operating system. That became sort of the standard system that a lot of the computer science researchers that were funded by DARPA around the country all used. And it became pretty important for the development of the ARPANET later on. And also a sort of a new industry arrived. So timeshare, this is the idea of the computing utility, which is that instead of buying or owning your own computer, you would actually rent time on a remote computer through timesharing. And so a company called Timeshare, which was actually headquartered in Cupertino here in Silicon Valley, was founded to be part of this new market. And you can kind of think of it as an early version of cloud computing in a way. Like it's kind of conceptually sort of similar, even though technically it's very different. So, time sharing kind of naturally led to the development of networking, actually. So, if a lot of the users that would be on one computer that would be sharing time on a computer, you could actually leave messages for the other users on that computer. And that became an early form of email. And, Licklider sitting, I think it was actually Bob Taylor who was, either Bob Taylor or Larry Roberts, who was the director of ARPA at the time. But because ARPA was funding so many different computers at different universities, they actually had multiple terminals in their offices. And so in order to log into this computer, you had to go to this terminal, and log into that computer, you had to go to that terminal. And so the director kind of thought, well, wouldn't it be great if I only had one terminal and I could use that one terminal to log into any one of these computers? And so the idea of connecting all of these different computers that ARPA had already funded, and having them share resources with each other so that ARPA wouldn't have to, fund multiple computers to do the same thing at different universities came up. And so that was sort of the birth of the idea behind creating the ARPANET. And in the interest of time, I won't go into any more detail than that, but there's a lot of good histories of the ARPANET and how that later on led to the internet. But I will now move on to discuss Doug Engelbart.
Oh yeah.
So Doug Engelbart, he was also working on computing in the 1960s, and he was at Stanford Research Institute. And he was very influenced by an article written by Vannevar Bush in 1945, just after the war. This article proposed a machine called the Memex. And that was sort of like a desk that had microfilm in it that would house the world's knowledge. And you could follow through the microfilm, you could actually follow cross-references between various texts. So it really posed the idea of hypertext in Doug Engelbart's mind. And so eventually with ARPA funding, Engelbart at SRI was able to start a lab and create a computer system called the Online System, or NLS. And this is part of his sort of larger plan to create a computing system that would augment the human intellect. So NLS was very famously demoed in 1968 at the Fall Joint Computer Conference in San Francisco. And there's some really fascinating videos of this. One of its major innovations, of course, was hypertext. It also had multimedia. It mixed text, graphics, and video together. It was also a collaborative system. So, long before Google Docs allowed two different people to collaborate at the same time on a single document, people were doing this on NLS. And it's also, probably Engelbart's most famous for having invented the mouse. The mouse was a critical component of the NLS, but of course, it was just a component of NLS. Engelbart didn't really see the mouse as the main point of the whole thing. The NLS was also on the ARPANET. It was actually the network information center of the ARPANET. So it was actually a very key node of the ARPANET. And it was based on an SDS 940 time-sharing mainframe. So the NLS was very influential on this next place that I'm going to talk about, Xerox Park. So Xerox, the copier company, decided to get into the computer business and bought Scientific Data Systems, or SDS, in 1969. And along with that, they decided that they needed to start a research center. And they decided to locate that in Palo Alto. So Park is Palo Alto Research Center. And the key person that they hired to sort of lead Park was Bob Taylor, who had been the director of ARPA's IPTO office. And through Bob Taylor's connections in the computer science community, he was able to hire a lot of the latest and greatest people, upcoming researchers in the industry. And so that included aforementioned Butler Lampson and Chuck Thacker. They had just been winding down a failed computer company called Berkeley Computer Company. That was sort of their attempt to commercialize their Project Genie time-sharing work. And so they got quickly snatched up by Park. And in addition, Park was able to essentially steal a whole bunch of Doug Engelbart's lab researchers from him, including Bill English, who was the co-inventor of the mouse. Another notable hire was Alan Kay, who had done his PhD at University of Utah. So Park is probably most well known for a computer called the Xerox Alto. This was designed primarily by Chuck Thacker, Butler Lamson, and several others. And it's very notable for being a computer that really featured a bitmapped graphics display. So what bitmap graphics is essentially what we all have today, right? Where the screen is essentially drawn in rows of essentially of pixels, and those pixels, the values of those pixels, whether they're black or white or whether they're color, those values are stored in the computer's memory. They're directly mapped into the computer's memory. That's where bitmap comes from. And this was actually fairly unusual at the time because most graphical displays that use CRTs were called calligraphic displays, or what we might call vector displays today, which meant that the electron gun of the display, instead of just drawing lines and drawing dots, it could actually be directed to draw a shape, a full shape. So you could actually draw like triangles directly using the electron gun. And that was really great for certain scientific applications. But in the kinds of things that Xerox was interested in, Xerox is a copier company, it's a paper company. It's a document company essentially, and that kind of thing isn't actually that good for documents. Bitmap graphics, however, is actually good because you can use bitmap graphics to represent text or graphics. And so one of the things that came out of that is the first sort of word processor that worked in what you see is what you get form, which means that when you look at the screen, what you see on the screen as your document will be similar to what you print out on paper. And so that meant that you could actually see the fonts, different fonts in your document file. You could use different styles, bold, italic, etc. Prior to this, if you were editing text documents, you would generally use different codes to represent bold or italic. So similar to like the way that HTML works, for instance, where you have to actually use codes to designate whether something is bold or italic, rather than actually seeing it directly. So this first WYSIWYG word processor, Bravo, was created by Butler Lamson and a man named Charles Simonyi. And Charles Simonyi later brought this idea over to Microsoft and created Microsoft Word. So Microsoft Word actually has its lineage going back to Xerox Park. The Alto was, part of this larger vision that the researchers at Park had about what they called personal computing, and which meant that instead of sharing time with a bunch of other users on a time-sharing mainframe, which could actually get really slow if there were too many users, instead every individual user had their own computer, their own workstation in front of them, and they had this very high bandwidth graphic display. And part of the bitmap graphics is that it was so memory hungry that it actually took over 50%, maybe even up to 70% of the computer's memory to represent those graphics. And this was sort of counterintuitive at the time, because you would think, well, why would I use that for computing purposes? Why would I actually devote that much memory to just displaying things? But it was very important for the researchers to do that, because they saw the Alto as sort of a prototype for not computers of the day, but for computers of the future, for 10 years or 20 years down the line, how people would actually use computers. So that's, if you look at the screen there, the screen is actually the shape of an 8x11 sheet of paper, right? A letter format sheet of paper. So that's actually very particular. The Alto also represented not just personal computing, but also distributed computing, because the Altos were also networked together in a local area network using Ethernet, which was created by Bob Metcalf and Dave Boggs at Park as well. In addition to that, Park also invented, Gary Starkweather at Park invented the first laser printer. And so at Park, you could actually write up your document on the computer, send it over the network, and print it all in the same laboratory. So essentially, Park invented the modern office as we know it today. And so some of the ideas behind device-independent graphics were also pioneered at Park. John Warnock and Chuck Geschke were at Park, and they later founded Adobe. And probably the next thing, the next most famous thing I'm going to talk about the Alto is actually the graphical user interface. So Smalltalk was a system created by Alan Kay and his learning research group at Park. And this was a system that was initially designed to be used for children. So Kay had very particular ideas about computers as not a tool, but a medium, and a dynamic medium, a medium that people should actually be able to change at will and be able to explore with. And he thought that this would revolutionize education. He created a concept for a tablet type of computer called the Dynabook in the early 70s. And so Smalltalk was sort of his way of exploring those ideas. And so Smalltalk has sort of the elements of the graphical user interface that we sort of think of today. It had overlapping windows, it had a desktop metaphor, pop-up menus, icons, and scroll bars. It was also not just an environment and a system, but also a programming language. It was an object-oriented programming language. That term was actually coined by Alan Kay. And probably the most famous thing about Smalltalk is this was the system that Steve Jobs saw when he and a delegation from Apple visited Park in 1979. So that brings us up to the Macintosh, and so I think what's commonly misunderstood about this famous Steve Jobs visit is that Xerox actually had a reason for inviting Apple to see Smalltalk and the Xerox Alto, and that was because, for one, a lot of this stuff, Xerox Park being kind of a research-oriented organization, they had already been giving presentations to various people already. But another reason was that Xerox had actually made an investment in Apple stock. And so this visit was kind of part of that business relationship between the two companies. So what ended up happening, I think a lot of people know this story, but Jobs couldn't believe that Xerox wasn't doing anything with this technology, and he was sort of blown away by it. And when he got back to Apple, he basically told the team that was developing this computer called Lisa to kind of scrap some of their existing plans and to basically base the Lisa off of this new graphical user interface technology that he had just seen. And the Lisa was released in 1983. It was cost $10,000, kind of overpriced, so it didn't do very well. Xerox actually itself had already released a computer called the Xerox Star, which also had a kind of a graphical user interface in 1981. That also was overpriced and also didn't sell very well. But after he eventually kicked Raskin off of the project and took over the Mac project himself, and turned the Mac also into a graphical user interface based machine, but much less powerful than the Lisa and at a much lower price point. And so that came out in 1984. The Mac itself was somewhat successful initially, but not that successful. And in fact, it actually started, sales actually started to really go down in 1985. And that's actually what led to Steve Jobs' leaving the company, that famous boardroom coup. And the Mac was actually only saved because of a new software application called Aldus PageMaker, which when combined with Apple's laser printer called the LaserWriter, and software from Adobe called PostScript, running on the Mac, created this new field called desktop publishing. And this allowed a user at home to create their own newsletters, newspapers, magazine articles, and print them themselves on laser printer. And this sort of cemented the Mac in sort of this creative professional role. So I think I'm out of time there, and I will end the lecture there with the Mac.
Thank you, Hansen. So we want to leave 5 minutes for a question for Hansen on anything. If you have questions, please, you can put it on chat or just unmute yourself.
I'm gonna stop sharing here.
Let me see.
Hi, Hansen.
Hi.
My name is Gary Ho, and I have 2 questions for you. In general, in the last 30 years or so, how much credit would you give to games and gamers in the development and advancement of computers? And my second question is, have you heard any evidence that Microsoft included Solitaire and Minesweeper with Windows 3.1 to sort of get people accustomed to using the mouse and to right click?
I guess I'll start with that second one. That's the first I've heard of that. So that may be true. I don't know. That's very interesting. That would be very interesting if it was true. So you mentioned the world of games and gaming in development of computer technology. Did you mention, you said the last 30 years, or how far back?
Yeah, since maybe the 90s.
Since the 90s? Yeah, I would say it's, I would say it's probably been pretty important. I think the most important thing is probably the development of the GPU. The GPU, was really developed for the gaming market, right? For the game enthusiast market. And nowadays, of course, GPUs have become important in AI, in machine learning, and for things like Bitcoin mining, for instance. So GPUs have become really important for a lot of other things other than just gaming. But really, if it hadn't been for the existence of GPUs that you could buy off the shelf, at a just as a consumer, this really was a breakthrough for AlexNet, which was the neural network, the deep learning system that won this ImageNet contest for image recognition and pattern recognition in 2012. And that sort of broke open the gates for deep learning, and showed that everybody that neural networks really was better at this task, given enough data, number one, which the ImageNet database provided, and number two, given enough compute power for matrix multiplications, which the GPUs provided. So prior to that, if you wanted to do this, I mean, you probably could have built your own custom computing hardware to do this, but it would have been much more expensive and would have taken a lot more grant money to do something like that. So, that's that's one area that I think the games industry is really transformed computing in the last 30 years. That's probably the biggest one.
Thank you, Hansen.
Thanks.
Great, thank you. We are out of time. Thank you so much, Hansen, for being part of our community day. And please keep us posted on the Computer History Museum's progress and opening.
Thank you. Yeah, we still have events coming going on. So please check our website for the latest events. I think we have one coming up soon with the New York Times journalist Cade Metz. He's going to be talking about his new book on AI and neural networks called Genius Makers. And so that's coming up, I think in a week or so, actually. And I think we have another event about asking the question, is AI racist? And that will be, I think, next month. Yeah. So, and we also have our Fellows event series. So we have a Fellows Award that we give out to luminaries in the field every year. And this year we have 4. We're actually, instead of doing one event for all 4, we're actually going to do one event for each one of them. And we just actually had one just last week for Ray Ozzie. And we'll have our next one for Raj Reddy, who is an AI pioneer, in June.
Great, thank you. We need to head out to our next session, so appreciate it. Thank you so much, Hansen.
Thank you.
Thank you.